let's just make do with what we got, right? So I guess the first thing I want to say about this problem is that when you start trying to draw a diagram, what you quickly realize is that the problem statement is symmetric in A and B. So I'm gonna make sense, I think, to draw a triangle. Well, draw this A and B first, and once you draw P, well, I'm gonna start by drawing A and B vertically because, not vertically. I'm gonna draw A and B horizontally because I want to like make the symmetry more obvious in my diagram. So there's AB, that's how we start drawing the picture. And the second thing you notice is that, well, once I draw the point P, the rest of the diagram is uniquely determined. So let's put down the point P somewhere. And so now I have to actually do some stuff. So we're going to call this 2A, and we're going to call this 2B. I used A and beta. That seems silly. I'm going to use B. Okay, so, well, what's going on? So if I'm going to try to draw an accurate diagram, then what I need is this angle here should be A, and this angle should be 3A. So, yeah. Alright, so C will be around there. Obviously I'm like kind of freehanding this. We'll see how well that turns out for me. So, oh man. Alright, I tried. So there's ABCD. And then the problem asks you to show that certain angle bisectors are concurrent. And so... Oh, that's... I think the left one's a little off. Should be more like that. That. Okay, so apparently these guys are supposed to concur. And... it's hard for me to do this completely fairly because I know what's supposed to happen. But what I'm going to say is that, well... Hi, are there no problem requests today? Probably not, unless people really want to do math. But by default, I'm probably not going to do much math today, other than... Yeah, this is mostly going to be just IMO presentation. So, well, you look at this picture and I'm like, you know what would be really nice if it was actually true, even though there's no way it's true because that would make the problem really silly. Big magical claim. Concurrence point is the circumcenter. And there's a couple of reasons why you might suspect this is true. One is that, like, it's on the perpendicular bisector of AP. The other is that I think if you really don't know what to do on this problem, like, you should draw the diagram properly. As in, like, on the IMO, I think the correct thing to do is actually have your ruler and compass and, like, start with PAB, mark, bisect the angle, copy it once, copy it 3 times, do the same for B, and then draw the thing. The nice thing is that because it's a concurrence of 3 lines, you have a tiny bit of built-in redundancy, so even if one of them is off, you'll kind of still have a sense where that point's supposed to be. Great. Yeah, so, wonderful. So now that we have this claim, we're going to make the following amazing observation, which is that 3 plus 1 is equal to 4. So this angle here is 180 minus 4a. And then this angle, well, I'm drawing in the circumcenter. This angle is what? This angle is also 4a. So that implies that these points are cyclic. And, well, because it's cyclic and it's the circumcenter, these are equal. So once we have CPOB cyclic, since OP equals OB, we're done. And that's it. Yeah, I think that's all I have to say. Yeah, so The entire difficulty of this problem is realizing what to do with the point O. I also... Oh, 3 plus 1 is equal to 6. Yeah, that will kill you on this problem. Yeah. I think the other thing... Well... The other thing that's interesting about this problem, and this is going to be a very common theme in day 1, is that... Like... I'll put it this way. This problem did not... remark, this problem does not fulfill its full potential. What I mean by this is that... Let me talk a little bit about puzzle hunts. When you have a puzzle hunt, when you design puzzles for, like, say, MIT Mystery Hunt or whatever, there's sort of this general principle that you don't want there to be extra information. Like, you want to set the puzzle to, like, sort of be quote-unquote perfect. And so, for example, when you're writing a puzzle hunt, if you want to give someone a set of items, you always put that set in alphabetical order unless the order of that set matters. If you, like, put it in a random order, you've added in some extra information that you don't need. You don't want to do this because it makes the puzzle less fun. So, when you design a puzzle, for example, you actually destroy information so that people don't go around chasing things that are, like, you know, not the intended solution path. Whereas this problem has sort of done the opposite, where because the only fact used about 1 and 3 is that 1 plus 3 equals 4, like, this problem would have been true if I replaced 1 and 3 with 2 and 2, or like half and like 7 halves, or any other combination. Like, the angle condition each angle condition is 1 degree of freedom stronger than it needs to be. Because the only thing that matters about the point C is that it's supposed to lie on the blue circle. So, this is how you can make a problem hard in a very artificial way, by, like, you know, this. Did I look at DP Puzzle Hunt? No, I didn't get a chance. I really wanted to, but I didn't have time. Yeah, so that's IMO 1, where, you know, this problem did not live up to its full potential. And so now let's go on to problem 2. I say full potential tongue-in-cheek, just in the sense that, like, you had the extra degrees of freedom, so you probably could have made the problem do a little more than what it actually did. Like, because as a problem designer, you had, like, a little more space to play with that you didn't exploit. Cool. So, I want to tell you a story about this problem. Once upon a time, 8 years ago, I was a little kid, and, you know, people were interested in these things called inequalities. And a very long time ago, I came up with the following idea, which was that, I'll tell you what it's called. It's called IMO 2013 Problem 2. And, well, so, yeah, so what happened when I was setting this problem, this is actually 8 years ago, sorry, I'm lying, because this Almo took place in June, so this was about like 8 years ago. And the idea was that in the Almo problem, I had this weighted AMGM idea, where I originally was thinking, well, if I have A plus B plus C times A, this has these A to the A, B to the B, C to the C. But, and here's the but, if I put an exponent on this A, then I get RA, RB, RC. And if you choose the value of R correctly, you will get the Elmo 2013 problem. That was the idea. I was like, not only can I take this weighted AMGM, but I can push it one step further and, you know, put this exponent on it and then spin it. So when I saw this problem, I was like, aha, it's back. And so what I wanted to do was, I want to use weighted AMGM where what you do is, I want to say cyclic sum of A plus 2B. I was like, this has to be it. I have these denominators, and so what I'm going to do is I'm going to put some weight here, and then I'm going to put some weight here, and it's going to be wonderful. I'm somehow going to get something less than or equal to 1 on the left-hand side. Somehow. And on the right-hand side, if I can get a to the a, b to the b, c to the c, d to the d, that's it. I'm like, that's why this denominator is here, because I'm here to like do the weights. So I tried this for a while. And the problem when you try this is that, here's the thing, like, let's say I like put like, let's just say as an example, I put like, what's the word? 2b or something. Well, then what you get on the right hand side, you'll end up with like a b to the 2b, which is not great. And in fact, what happens is that, okay, well, maybe I can fudge the weights somehow. So, because the weights add up to 10, so I really want the exponents to add up to 10. And so, you know, how would I do this? Maybe I have like, you know, let's say maybe the d weight is like 4, and this one will then be like d to the 1/4. That's really sloppy. But then when you look at this, well, what happens is you end up wanting to show something like a to the a plus b to the b halves plus c to the c thirds plus d to the d fourth. Is that right? No, I'm definitely messing something up. Oh, there's even coefficients. So you end up wanting something like this, and this is like false. No, doesn't work. So that's a little unfortunate. And I'm like, okay, well, and I tried a lot of other things, but the problem is that everything I tried, I think this music is a little too energetic for this problem. Everything I tried, like, either ended up getting me like b over 2 to the b, which is not good because I really don't want to deal with 2 to the b, or like it just wasn't true. Like this is false and so on. So after a while of doing this, like I was just like, this sucks. It's not working. Like I don't know why this denominator is here, and I know I'm missing something. So what I instead do is I'm like, okay, you know what? What's the simplest thing that could happen? So then I went and said this inequality that, you know, people just know, a to the a, b to the b, c to the c, d to the d is at most a squared plus b squared plus c squared plus d squared over a plus b plus c plus d. And I was like, you know, this is so bad, like there's no way this is true. And so I plugged it in, and I was like, what happens if that I do this? I get a plus 2p plus 3c plus 4d. I want to be less than or equal to, what is it? So at this point, you homogenize it, so it's degree 3. And on the bottom you get that. How do you get that? Is it just by, yes. So the way to AMGM in the IMO problem, you take r equals 1 and you get the thing. So what I mean, like, I was just like, okay, well, like, what happens if I tried this not thinking it would work. I wanted to see how sharp the inequality was to get a sense of like what methods I should be trying on the problem. So I was like, okay, like, if I just replace a, b, b, c, c, d, d by this fraction up here, what would happen? And so I took the IMO problem. I went with the squares because I could have picked any exponent, but that if I picked a different exponent, it would cause this to gain a power, and I really didn't want it to get a power. So there. And I was like, okay, well, this inequality is obviously not true, right? Because if I just take a equals b equals c equals 0 and d equals 1, it's false. And then I was like, wait a minute, a is at least b at least c at least d. You know, I first thought this, yeah, so like this won't work, the inequality is not close, and I'm like, wait, d is the smallest one. And then I looked at this and I was like, d? 4d cubed? And I was like, if I expand this, actually, the left-hand side might actually be really small. Because you look at it as like, you know, my counterexample was here, but if I sort them, it goes the other way. Like this 4d this D, it's like that left hand side is really small. The other thing is when I set them all equal, it's 40 versus 64. So that's when I was like, maybe this is not that far off. Maybe I can just expand and see what happens. So let's expand and see what happens. So no, I'm not using the buffalo, thank you very much. A cubed plus 2a squared b plus 3a squared c. I hope I don't make any mistakes. 4a squared d, and then if I do b squared a plus 2b cubed plus 3b squared c plus 4b squared d, c squared a plus 2c squared b plus 3c cubed plus 4c squared d. There's a d cubed here. D squared a plus 2d squared b plus 3d squared c. And then on the right hand side, I need to expand. So this is a 4x4. You just draw a 4x4 square. It's not that hard to expand. I mean, I have the privilege of having done this already, so I know what's supposed to happen. Oh no, that's gotta suck. Alright, so then here, the a cube is actually easier. It's the same table, but everything's a 3. So 3a squared c plus 3a squared d, 3b squared a, b cubed, 3 b squared c, 3b squared d, 3c squared a, 3c squared b, c cubed, 3c squared d, 3d squared a, 3d squared b, 3d squared c, 3d, no, just d cubed. I keep writing 3's for the cubes. They're not 3's. And then there's more stuff. There's 6abc plus bcd plus cda plus dab. Reinforcing small terms. Procrastinate grading IMO. Are you a leader or coordinator? Okay, so cancel. There should be a 4 here, so this should say 4. And this now says 3. And then, okay, there's a lot of 3's actually, so all these 3's go away. Shoo, 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 shoo. Then also, which ones go away? Bang, bang, bang. Gives me 1, 1, 1. This time this one, this is 1. Yeah, so if you put this in the table, it's actually much easier to expand. Did I do that right? What a mess. Alright, so yeah. If I did this correctly, what's left over, I was like, oh, there's actually not that many terms. So here, there's a b cubed. I'll put them in the same places in the table so it's easier to see. And now I'm looking at this and I'm really eyeing it suspiciously because d is the smallest one. This is not, your intuition from symmetric inequalities is flipped here. Where when you do symmetric inequalities, you're scared of d cubed. But here, d cubed is a good thing because d is known to be the smallest one. There's 6abc plus bcd plus cda plus dab. And then which terms survived the explosions? All the cubes died off. There's like... which things are still alive? The stuff on the lower left, right? So there's 2b squared a, 2c squared a, 2d squared a, c squared b, d squared b. Where's the last thing? A squared b. So, then I'm just like, okay, well, you know, there's so many D's. There's D everywhere. D, like, left hand side just has D. So let's just do this. Pew. This is 1 now. That's done. Let's take this and nuke that one again. Let's take this guy, nuke that guy. This guy can kill that guy. This guy can kill these 2 guys. This guy can kill that guy. We're done! And then these extra terms are just positive. We don't even need the mixed ones. So, this happened, and I was like, huh. What I wrote down in my notes is, I must have fake solved. I'll come back to this later. But it turns out I didn't fake solve, and this is actually what you're supposed to do. Like, I was just looking at this, because here's the problem. Like, you know, I made a remark on the previous thing where this problem does not fulfill its full potential. And the reason is that, well, this inequality has nothing to do with any of the given conditions. Even the condition that the sum is equal to 1 is not related to this. Like, it's this weighted AMGM, and then the expansion is just, you just expand. Like, I don't know what to say. Like, so I think the main thing that helped me was like noticing that there were a lot of D's. Like 4D cubed is really big, and so yeah, that happened. But KVED, I'll get to your question in a moment. But I think like by far the hardest part of this problem is like, I don't know, belief. I don't know if that's the word for it. I don't know. Honestly, like the reason I tried this is because I was fed up of the weighted AMGM not working, and I like. I just think like during the IMO, I'm not sure I would have risked it, because when you're actually at the IMO, then you know you can't just goof off anymore. Like when I was doing this, I was just like, you know, what's the worst case if this doesn't happen? It means I like wasted like half an hour of my life, or actually more like 10 minutes. But it's like I wasted 10 minutes of my life doing this expansion, and it didn't work because of course it didn't work. If you're at the IMO, you know, you don't just throw away minutes of your life, because those 4.5 hours really, really matter. So yeah, it would be funny if it worked. I honestly had the same thought as I was expanding it, as like, if this actually works, then I can make fun of the problem selection committee. Yeah, so we did it, team! Wait, does 1333 hold? Yes. Yeah. I don't know. Okay, so let's do problem 3. Alright, I need to ask Mose, definitely at least 25 for the inequality. I'll tell you this right now. That inequality you just saw is a 2-5 because it's so unbelievable that something like that would actually work. Is IMO 2015 5 or 2015 2 better? I like 2015 2 better, honestly. But that's just because I'm not a functional equations type person. Yeah, see. I mean, here's the thing. It's the IMO. You guys don't need to argue about the problem difficulty now. You can just wait until the results come out and then make fun of the people who got it wrong. Why is the inequality at the top hold? It's weighted AMGM. Okay, I better actually explain it. What happens is by AMGM, cyclic sum of A over A plus B plus C plus D times A. Why did I write 2010 as 25? I downgraded it to 20 recently. No, I didn't say who didn't solve it. I said make fun of the people who got their prediction wrong. You don't make fun of the people who don't solve a problem. That's actually mean. But the people who are going around saying that this problem is like a high school honors problem, you can make fun of them. Oh, that's fine. Yeah, so by weighted AMGM, this is at least that. It was B plus C plus D, and that is 1. Sorry, yeah, when I say the people who didn't get it, who got it wrong, I meant the people on the predictions thread. So don't make fun of the people who don't solve it on the contest. That's actually very mean. Do you think any of these problems will be notice units? So I've been considering for a while running a unit called Art School, where the point of the problem is, or point of the unit is that you do geometry problems where the most important part is that you draw a diagram that tells you what's going on. And IMO 1 is like poster example. TSTSD 2099. I feel that one's actually kind of hard though. Yeah. Okay, right, where was I? Okay. So, IMO 2023. So, I have to say, I was spoiled a bit on this problem because I was surfing the forums before I had solved this problem, and then I saw a post from, I think it was Yoni. Thanks, Nuke Launcher, for the 30-bit cheer. And the post said, chaotic evil. Number 3 is NT because 1 plus 4n equals 2 plus 4n minus 1 equals so on. And I was like, oh, are you serious? So, the biggest observation about this problem, I think, is that, well, this is the biggest thing. This problem does not live up to its full potential. And the reason is that the sum is kind of bait. Like, saying the sum is equal is about, you know. Yeah, we're just gonna do this. So here's what we're gonna do. So we have these n things. Da 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 da. And then we're gonna draw a string of like, for example, if I have 1 here and I have 4 in here, so this is like color 1, this is color 2. I'm going to take this string and draw a string between them. Should do 1 to 4n. And then you do the same, and then what you get is a graph. And maybe there's like another one, and then, I don't know. Then, oh no, that has an extra edge. So what I've done is I'm like drawing a bunch of strings between the rocks, and if I do this, what's happening is I get a graph. The graph looks like this. Okay, boink, boink, dun, dun, dun. Okay, so that's what's happening, and what does it mean to put it into 2 piles? That means I want to take the strings and put them into 2 different categories, such that every every string every vertex has like 2 strings in one category and 2 strings on the other. So I'm now going to repurpose the word color. Problem, given a 4 regular means that all the degrees are 4, multigraph G, find a 2 regular sub multigraph. So yeah, that's what's happening. So that's where we are, and this, I don't think I would solve this problem at the IMO, because I wouldn't be brave enough to believe that something like this would work. I don't think I would have just thought of the pairing idea. I was just like, you know, that's kind of the silliest way to deal with subs. But I saw this comment and then I was like, okay, really? And I was eating breakfast and I was like, okay, well, if this is really gonna work, what is a 2 regular sub multigraph? It's a bunch of cycles. Okay? And that got me thinking, if I have a 4 regular multigraph, well, 4 is even, so theorem, Euler, each connected component has an Eulerian circuit. What's a two regular submultigraph? It means I take a subset of the edges such that every vertex touch has two guys. Oh, when did I start getting involved in making problems and writing EGMO? I started writing problems around 2012-ish. Because that's when I started like suggesting things for Elmo. I started writing EGMO in 2014 because I was stuck as an office assistant because my school wanted to collect money for me being there and they couldn't do that if I was there only 2 periods a day. So they told me to be an office assistant for 3rd through 5th periods so that they could collect money for me being at school. So during that time I was very bored and I wrote EGMO. That's the story. Are there any prompts you would add to personal favorites in EGMO now? Yes. Quite a few. Because that book was written in 2014, right? There's like 5 years of more prompts I'd want to add. Okay, so Eulerian circuit. I started thinking about cycles because I was like, well, 4, I want 2. So that's fine. And then I was like, okay, if I actually do this, if I have an Eulerian cycle, will you update the personal favorites section if I ever publish a 2nd edition, which looks very unlikely because it seems like it's not worth the effort. Eulerian cycle, I'm like, okay, well, edge. And then I was like, wait, you can just alternate the edges. And this will automatically work because when I have a vertex, I originally wanted to just dissect it into cycles, but then I was like, wait, that's like a different thing. That's like a composition to cycles. But here, if I have if I go in and out of a vertex, then if I take this edge but not this edge or vice versa, actually it's a different color. Use this one and put the other one in the other color. Well, that's my half result. Like I can get half the things. And then I was like, well, okay, well, what if there's a self loop? Like that will mess things up, right? If I have a self loop like this. And the answer is no, that won't mess anything up because what will happen is you'll get the blue one here. And like a green one here. And then it's okay. And I was like, oh, I guess that just works. So let me do this on this graph as a demonstration. So I'm going to start here. I'm just going to use every edge once and then color them green and blue in alternating colors. And I need to be careful to not push myself into a corner while doing this. So that's blue. That's green. Am I stuck? No, not yet. Blue. Green. Blue. Green. Blue. And there you have it. Now I have the desired thing. This is the opposite construction as the code versus problem. Is there a good explanation for that? So I didn't actually read the code versus problem. What exactly is it? Yeah, I have to think about it. Is that an elephant? There's an elephant. What's the motivation for considering graph theory? Oh, I don't think it's considered graph theory. I think the motivation is called, let's just hope that I can do this pairing argument. And if you interpret the pairing argument, if you say, what am I trying to do? I mean, I drew this picture with the strings, and what I'm trying to do is I'm trying to take, like this is, the graph theory is a translation. Yeah, the motivation is called the drawing on the left. Like, I have these pairs. Still not sure I what graph you take so the weights are the same for the partition. So what I do is I take all the pairs, like 1 plus 4n, I draw a string between them. That's an edge. And then if I have like, here, I'll draw another one. 2 and 4n minus 1. These two rocks, I draw an edge between those. And yeah, how does one expect this to work? I don't think I would expect it to work. And I think that's what's so interesting about this day one is that all three problems have this property where like I feel like I don't have any reason to expect a priori that this should work. Like, leap of faith, I think, is a good way to put it. It's just like, I'm going to gamble my time at the IMO on this claim that might not even be true, but would solve the problem if it was true. And problem one less so. Problem one's a little more motivated because at least in geometry, like you have a diagram. Like you can draw the diagram and say, oh, look, it is just the circumcenter. Wow. But like problem two, I don't think there's any reason you expect that. There's no conceptual reason to expect the weighted AMGM to work, and for this problem, I think there's no conceptual reason to expect the pairing to work, except for the fact that the problem is really hard to do otherwise. Like, addition is just really hard to deal with. When you do problems like this, there's a whole field dedicated to, like, addition. Like, additive number theory, like this sort of combinatorial addition. Let me give an example. On the math prize for Girls Olympiad, the most recent one, so like last year, there was also a problem that had this flavor. Let's see if I have it. 2019 4, right? Yeah, it also had this flavor where you're trying to do like this additive thing, and this one's even just like, oh, actually no, it is subsets, and it's the same thing. Like when you look at the solution, it's not like, how do I say it? There's no deep facts about addition used. What they're doing is, it's actually a pairing argument. It's sort of a pairing argument. What they do is like for each addition, they like, Same thing as here, where like we did 1 plus 4 and 2 against 4 and minus 1, 3 and 4 and minus 2, pushed all the way towards the center. I think the same kind of thing happened in the math prize problem. Where you would take n and like some k with the same parity as n, and then like to pair them up to get the sums to be the same. Because additive number theory is hard. Let me make this clear. Like, addition is really difficult. The fact that this P3 was selected with, oh. Oh no. Okay, data calculator, can you like chill slightly? Oh wait, that's a shout out. Sorry, I'm rejecting that shout out. Yeah, no, like, additive number theory is also just hard. Like, graph theory is just that strong. Well, I just don't think the idea is graph theory. I think the big surprise is that you do a pairing. And in hindsight, like, I think what I should have thought is, what else am I supposed to do? Like when I was thinking about the problem, it felt like this thing where like there was just no plausible algorithm. Like it didn't. When I was thinking about it, I was just like, how are you going to do this? Like there's no plausible way to like deal with addition, and so you're supposed to like. I don't know. Are there a set of problems that you need to rephrase in terms of graph theory? I mean, I'd have to think about it. There's like a few I can think of, but like, don't think of it as a graph theory problem. That's like not the takeaway from this problem. The takeaway from this problem is the addition, like to deal with the addition by a pairing argument. And then you interpret, when you interpret the problem, you're like, the graph theory words don't matter. This is what I'm trying to say. Like, you get the graph, you read off the graph theory statement from what you end up with. The problem gives it to you once you push it the right way. Yeah. Like, you don't come up with the graph theory statement. The graph theory statement is given to you. That's what I'm trying to say. No. Shout out rejected. Okay, so let's go into problem 4. This statement. So, this is a problem that appeared. And problem 4 does not achieve its full potential. I agree, but I think at least it's not necessary to realize that in order to solve the problem or something. Like, I think in problem 2 and problem 3, you really have to believe in something that you aren't promised should work out. Whereas here, let me tell you my thought process for this problem. The thought process is like n squared. Like, why is n squared? Like, this problem statement has nothing to do with... There's no reason that this statement needed to have n squared in it a priori. Like, you're like, okay, well, there's some number of cable cars. Why should the number of cable cars be a square? That's like... Why? So... Here's what we do. We're gonna draw a square. And I guess I will, yeah, I'll elevate the square. Why not? So... Welcome to Mount something. I'm not sure what. The slopes of Mount Inequality, I guess. It can be like a black diamond ski trail. I don't know. I just was like, it's on a mountain, right? I was like, we should name the mountain. So okay, like, why is there n squared? And I thought about it for a while, and I was like, what construction would work? And well, now that I put it in a square, let's just make the cells. So this is, I think, the hardest part of the problem is to come up with this. This is a construction that works. And it's why, like, when I drew in a square, I was like, you know, okay, I have this grid, and then I drew in the grid itself, and I'm like, oh, this is actually a construction. Like, okay, that happened. And I was like, I saw this and I was like, this has gotta be it. This is the type of construction. Because it actually uses the fact that it's a square. So, k equals n squared minus n fails. And so, I just want to show that there is one more... if I have one more thing, then I'm going to break. Now, when I've done this, this graph naturally has some connected components, right? So we're gonna phrase it in terms of graph theory again. I'm sorry, but it looks like this, right? These blobs. And what I'm gonna do is, how are contestant numbers determined? Alphabetically. Unless the person inputting them messed up, but it's supposed to be alphabetical. Yeah, so if I have n squared k equals greater than n squared minus n, then the number of components in each of the cable cars, I'll even write connected component, in each of the cable cars is exactly, we'll do k is n squared minus n plus 1, is exactly n minus 1. So in particular, why is this statement so long? Let me shrink it a little. So in particular, like, some component has size, some red component, let's say, has size at least n plus 1, strictly greater than n. So some red component has has 2 or more vertices in each blue component, the end. The end. So, there is one thing about this problem that I found really strange, which is this condition that a cable car which starts higher also finishes higher. As far as I can tell, this condition is extraneous. Like, it's not extraneous in a way that hurt me. In fact, it's actually helpful. Oh, are you taking undirected components? Yes. I guess maybe this is why. Like, basically, each of the because of this condition, like each of the components is just like an ascending path. Like it just goes up. Yeah. There's no branches. Like every component is actually just an ascending path. It just goes up. That's it. So you don't have to think about connected in a directed sense versus undirected sense because they just all increase in height. You're taking almost as long as the IMO team that did not see the problems beforehand. Well, I'm trying to motivate the solutions. Why exactly n-1 components? Every edge you add decreases the number of components by 1. Shout out to IMO6 from Satsidhark. There's another Bizwadev shout out. I'll take the V-Bucks. Yeah, but every component decreases by 1. What can you do with V-Bucks? You mostly request problems. That seems to be the most common use. Oh, what can I do with V-Bucks? Oh, nothing. Not all stations have to have an edge. Yeah, that's fine. Is it true that IMO 6 had really slow solves? I believe that. It seems like this problem is really hard. Not sure how I see how this breaks. If I add a blue edge from 8 to 9, it violates the condition that where is it? Yeah, there's k different starting points and k different finishing points. Yeah, higher to higher I think is... It's useless, but I'm not mad about it because I don't think it hurt me, right? In fact, it actually makes your life easier by narrowing down the construction search space. And once you find the construction, you have a pretty good idea what you're supposed to do. Like, extra information can both hurt or help you. Like, in this case, I think it helps you, on average. Whereas, in the other problems... In, like, problem 2 and problem 3, it definitely hurts you. And problem 2, it definitely hurts you as well. Problem 1, I think it hurts you as well. Like, in problem 1, like, the correct natural statement doesn't include 1 plus 3 equals 4. Right? Like, the correct statement, the naturally correct statement for problem 1 is like, you know, it lies on the circle. Even ignoring, if you want to hide the circumcenter, fine, but like, the condition on the points C and D should have just been that, like, the angle was 4. But the author deliberately said it so that it was hidden behind this 1 plus 3. Yeah. Why is the statement 200 paragraphs long? It's graph theory, what do you expect? Okay, let's go on. Alright, IMO 5. So, here's what's up. It's mostly not combo, I think. Does problem 5 achieve its full potential? I think there's no obviously extraneous information, I think is what I would say. Why does mute me cost 384? Because it takes my attention. So, the very first thing I'm going to do is sort the numbers. And the reason is that because there's means involved, you automatically have some information about size. Like, you know, there's... Like, I expect size to definitely do something. The second thing I'm going to do is say... Actually, let me worry about that later. So, like, in particular, this idea about size will immediately tell you that something is up with A1 plus A2 over 2. Something is up here because this number is too big to really be a geometric mean of anything. So for this to be a geometric mean, some things... There must be an A1 in here somewhere, right? Otherwise the number is too small. Where by A1, like if A1 equals A2, I let that happen too. But like the maximum number should appear. Now you can keep pushing size on this, but the moment you see this, like something should already feel wrong. Because what I can do is I can look at a prime P. And if P divides A1, then this is a geometric mean, so P will have to divide this whole thing. And if P divides the whole thing, but P also divides A1, P divides A2. So, conclusion, like, P divides A1 implies P divides A2. And at this point, I think the main mistake you can make is try to chase VPs. Like at this point, you're like, wow, I have a lot of VP information. Like, you know, there's some stuff here that's resolved by P, blah, 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 blah. That's not what you're supposed to do. What you're supposed to do is like stare at A3 because you are like, well, why don't I do the same thing? And this thing better have like A1 or A2 in it. So whatever prime I had that divides A2, well, A1 and A2, this prime P is in here as well. And so P divides this whole thing, but P divides A1, so you get A3. So P divides A3. And now, well, if it works once, do it again. So I repeat, and when I repeat, yeah. So P divides everyone. And now if like a prime P divides everything, you pull it out, like you just divide it out. And you keep doing this until there's no primes left. Once there's no primes left, A1 equals 1. And so all the numbers are 1. Can you make an extremal principal NT unit? I don't want to. Unrelated, was there 5x squared plus minus 14? It was 5x squared plus minus 4. And the reason is like, this is like exactly an example of a problem where I do not want the student to say the lesson I learned from this was to look at the configuration with minimal sum. Right? Because that's not the idea. The idea is like you just find that if there's a prime P that divides A1, it bubbles through everything. Why would I make an extremal NT principal unit? What would I put in it? Like the problem I have in the extremal with extremal is definitely not this problem. There is a size idea, I guess, and it's that the arithmetic mean is big, but that's just a size and NT idea. I don't think I would call it extremal. I would just say you should have size in your head because there's a mean. That weird combo we did in stream once. I don't know which one you mean. Yeah. No, but the thing about this problem, why are people calling this P5 combo? Because it's fun to complain that there were 3 combo problems. I guess. Can you do a USAMTS test review? Well, I haven't done any of the problems, so no. When I mean the deadline is over. Or, like, I haven't looked at the... Oh, I see. You want me to look at the problems. Maybe. What if cube root a1, a2, a3 is a1 plus a3 over 2? That's fine. Like, my point is that there needs to be a number that's, at least a sub 2 inside. Even if a2 equals a3. But, like... Stuff. Here's the USMCA problem. Oh, man. I feel so bad about that problem because it's the one problem I didn't test solve because it got replaced. They gave me a draft of the test and then one of the problems got replaced by this one, so I never got to test solving it. And then it turned out to be the one broken problem, and I was like, oh, I'm so sorry, guys. I should have looked at the replacement problem. I test solved that year's test. I don't test solve every year, but that particular year, I got invited to test solve. Alright, let's do the killer. You're hoping I would try it and fail and wonder why. Alright, so... This problem is so hard. Yeah, I like problem 5 a lot too. I think the result was like very fun to prove. I have a hard time judging its problem difficulty of problem 5 because I was spoiled on it because I'm coordinating that problem. But anyways. Alright, problem 6. So I think the first thing I want to talk about is projections. And what I mean by projections is this is what the we'll say let R be a number. R be such that... Well, okay, let's say... How do I want to do it? Let's just assume... every separating line is within n to the minus a third. Asymptotically. So the first thing I want to talk about is about projections, which is that the right way to think about the problem, I think, like the correct phrasing, is that you want to say, I have these points. Points, point. And what I do is, really what you want to do is think about what direction do I want to project these lines in? Because you only really care about the direction. Why do I say this? Because here's what happens. I want to take all these projections. And what is the problem hypothesis saying? The problem hypothesis is saying that like all of these should be less than like Cn to the minus 1/3. Do I want to write? I'll be careful with the consonants. All right, I'll make things easy. It means that any direction I project in, choose. So you don't have to think about the separating line itself. I think what you do is you think about the projections. You look at where the shadows of the points are, and you want to show that there's, you want to get something to blow up. So the big idea behind the official solution, and the thing I don't think I would have come up with, is this is where you actually call it extremal principle. What I'm going to do is I'm going to look at the longest line segment AB. You look at the two farthest away points. And the reason you do this is because now the points are trapped inside this big intersection of two circles. You know what I mean? What do I classify as write-up mechanics? Things that don't help you find the main idea of the problem. Can I make unit of problems that are hard to write up? I'm reluctant to. I think like in Olympiad culture, very often people use hard to write up as a euphemism for hard to work out the details. Yeah, like I have like unusually little sympathy for people who say they solved the problem but couldn't write it up. I know, like there are cases where these exist, I think, but they're a lot rarer than expected. People in correspondence get Discord, yeah. Most people are correspondence because I can only give so many lectures. Okay, so back to this. So we're taking this big segment, and the perk of taking the big segment is that you know from the problem condition that there's a point whose shadow is like every so often. Like the shadows are all close, so there's tons and tons of shadows that are here. Oh no, 2018-3 is not. See, that's also me abusing. 2018-3 is, it's hard to get that calculation to finish. It's not about writing up a calculation, it's about doing the calculation. Area argument? Oh no, that's not what we're gonna do. This is what we're gonna do. So what I'm gonna do is I'm gonna, you know there's points everywhere. So now I'm gonna take this little snippet, cut it right here. And I'll pick any number here. I'm gonna pick any number less than 1 will do. So I'll pick like 1/2. So you know there's a lot of points in here. There's like, there's a lot of shadows. There's shadows everywhere because we're assuming that all the shadows are close together. Right, so there's a bunch of points stuck inside this little region. Their shadows lie on this little snippet. How many points are there? About like Cubuden-ish. Okay, I'm gonna start being lazy with this. There's at least like cube root endpoints here. On the other hand, how long is that? Well, how long is this segment? This segment is like, let's see, if I have endpoints, their shadows were like, because these shadows were like n to the minus 1/3, and there's n of them, this is like n at most n to the 2/3. So what you do is, yeah. So you either, now what you do is you project the points this way instead. You project them this way. And the problem is that there's, sorry, what am I saying? Okay, well, let me say what this thing is. This length here, this purple guy, has length equal to root. If I call this radius r, let's just call it r. R squared minus r minus 1/2 squared. So when I simplify this by the Pythagorean theorem, the extent of all the geometry I'm going to do this problem, it's like, shoot, what is it? R minus a quarter. So let's see if alright, so on the one hand, in my 1/2, I expect that there are a lot of points here. So there's a bunch of points. A bunch of points? Yeah. And on the other hand, this one is also long. Wait, that's not what's supposed to happen. Yeah, let me check the solution. I remember this is what you were supposed to do. You count the number of points and... Yeah, it's too... I want to say it's too long, right? So I had r length. I want the radius actually to be big. I assumed this was the biggest length possible. So it's like there shouldn't be enough points. How long is r? I have n points. The shadows are all n to the minus 1/3 long. Why do I have a lower bound on r? Why do I have an upper bound on r? I want a lower bound. Okay, what did I do? Blue segment is not that long if the circles are small. Well, the thing is, I want the blue segment to be long though, right? Am I flipping it? It's like I want the blue segment to be long, so there's a gap. What am I doing? No. Oh, I see. The blue segment is not long enough. Fine. Okay, I get it. Okay, so the number of points is like large. It's like the number of points is at least cube root, like on the order of theta cube root n. This segment is is not that long though, and so I have a lot of points and yeah. So this segment, the blue segment, can be at most, because the shadows are spaced every cube root n. Like these shadows are here, so this blue segment is less than or equal to okay, wait. I'm flipping every sign. It's just exactly the kind of thing I do. So where's the theta cube root n coming from? This tiny segment here is a segment of length half. There's like a 1/2 length here. So because the shadows are close together, that means you need like omega. Yeah, I'll write omega. Honestly, when I'm doing my scratch work or something like this, I just leave out all the Greek letters. Just write like cube root n. So there's a lot of points here, and the projections. These projections might be farther apart because there might be more points. Okay, there might be more points out here that have like projection there. But what am I doing? Where's the cube root n coming from? Which cube root n? The number of points? Like I have a segment of length 1/2, so there's the hypothesis of the problem is that every two shadows are within cube root n of each other. So the point is that this region here, like there's a shadow every cube root n at least. 1 over cube root n. Right? So we're assuming that right. We're assumed that any two shadows are within cube root n. Yeah, we're assuming that. We're assuming we're done with the problem? No. The problem is asking you to show that there's at least, you can get a shadow which is at least cube root n apart. Like, right? Is this the first or second problem? This is problem 6. Oh, this is the this is problem 6 of the stream because I've just been doing IMO 2020 and it'll be the last one, I think. Right, so what am I trying to do? Oh, this is so bad. I might not post this on YouTube actually, because I'm messing everything up today. Oh, Jesus. Alright, what did I mess up? Yeah, so there's at least... Okay, so this one is at most... What am I trying to do? It's half a stream. We didn't live solve anything today. Okay, sorry. I'm being silly. So here's what having a long segment accomplishes. So I think this blue I think I want to do it this way. This blue segment here is at least 2/3 ish, right? So this is at least like omega of n to the 2/3. at least. Sorry, at most. So I should write big O. Okay, there we go. I see what's going on. So this blue segment is at most O of n to the 2/3, right? By Pythagorean theorem. The blue segment is not that long. There's a lot of points in this region. So what I want is I want some of the points in this region to have shadows on the blue line that are close enough together. And here's why. When I look at 2 points in this critical region on the left, their shadows actually cannot be very close. Right? So you might imagine maybe the shadows are close. So what does that tell you? But there isn't. And the reason is that we picked this guy to be less than or equal to 1/2. So because the region is so narrow, all the shadows have to be like, these have to at least be √3/2. So here's what happened. I narrowed this strip because the shadows to the x-axis are close together. There's a lot of points in here. There's cube root n points in here. Also, because there's shadows all the way along AB, this whole radius is at most like n to the 2/3 ish. So this blue segment is pretty short. Not pretty short. This blue segment is not too long. I have a lot of points on a not too long segment, but the corridor is so narrow that the gaps between the shadows have to be pretty big. The gaps between the shadows in particular need to be at least like √3/2. And so from that, so you have, so the blue segment is length about n to the 2/3. There's n to the 1/3 points, and the shadows are at least √3/2. So like 1, quote unquote, apart. Oh, sorry. N to the 1/3. This is 1. Sorry, this is like square root. So R is 10 to the 2/3, so this segment is at most n to the 1/3. There we go. And that'll do it. So this is, yeah, the length of the blue segment is too short to accommodate the shadows being √3/2 apart. And once I push the constant c sufficiently small, this will work. Man, what a mess. Alright. Can you find a constant c? C is 1/8, I think, according to the official solutions. Yeah, this problem is really cool. How is the blue segment determined? So AB is the longest segment, and then you step over by 1/2 and then draw this perpendicular line. Should be blue length at least n 1/3. Yes, sorry. Yeah, this should be √R is n 1/3. Did this problem achieve its full potential? I think so. There's no obviously superfluous information, and actually, I believe that the result is sharp up to a factor of log n. Like alpha equals 1/3 is actually the optimal constant, is my understanding of the current state of the research. Didn't people say that, why must cube root n dots be left of blue? Because we're assuming that any two shadows are within cube root n of each other, so there's like a 1/2, like there's this 1/2 length, right? And what you're saying is every 1 over cube root n, there's at least one shadow. So the number of points is at least like constant times cube root n. Doesn't it say the Mohs document is for fun and people shouldn't take it seriously? Well, yes. That doesn't mean people are going to listen to me. When are the results released? When the IMO finishes, I guess. How much would they give for alpha 1/2? Not a lot, I think. Almost. When will Spring apps open? Oh, I don't have Spring apps. Like, there's just the rip. There's just the... Yeah, so, okay, people seem a little confused. So to summarize, so... I'll say it this way. Assume for contradiction that any two shadows let A, B be maximal segment, and draw blue line half right of A. Then we encounter a shadow every cube root n. I'm just gonna leave off all the constants. So at least n to the 1/3 points of S to the right, to the left. On the other hand, AB is less than or equal to n. You know, you can keep encountering shadows, but you only have so many points. So this is n to the 2/3, and by Pythag, blue segment is at most n to the 1/3. But the big important thing is that when we take far points in our trapped region and project them onto blue line, the length of the shadows, or the shadows must be at least √3/2 apart, because the region is so narrow that you can't spin the points so the shadows are close. I assume you can make it more sharp if you fiddle with 1/2. Yeah, I don't think 1/2's optimized. It's just like literally. How do you get c equals 1/8? This solution will get c equals 1/8 if you actually work out all the constants, which I'm not doing. But log n, I don't know. That's just something I heard at secondhand. Among Us. How does the Pythag work? You compute it. Like by the Pythagorean theorem, it's square root of r minus 1/4. Because r is about n to the 2/3, the square root is like n to the 1/3. Yeah, the c should appear everywhere. I just like dropped all the constants, like because I'm only interested in the asymptotic. Oh my god, geometry scribble, really? Can you do Lester's? Probably not. I'm probably not doing any math today. Just IMO review.